Here's an example for class 16 out of Borgnacki, problem 480. An initially empty canister of volume 0.2 cubic meters is filled with carbon dioxide from a line at 800 kilopascals, 400 degrees Kelvin. Assume the process runs until it stops by itself and it is adiabatic. Use constant specific heat to find the final temperature in the canister. And then we also have the next problem. It says repeat the problem, but use the line condition of 800 kilopascals, 20 degrees Celsius, and use table B.3 to solve it. Let's see how this works out. All right. So let's see, the volume, 0.2 cubic meters, and starts out, it's on a line, right? So when they say it's on a line, what they mean is there's some kind of supply, and we have a valve right here. And here's our canister. So the supply always maintains the same pressure and temperature, right? So the conditions in the line are the same. So that's kind of like the code words that they're using as part of this. And it's kind of weird how they changed from Kelvin to Celsius right there. I just noticed that. All right, so, and this thing was, is the volume. And then, so we might want to take a look at the properties. So we took table A5 for CO2. I won't use that one very much for problems. That's 0.1889 kilojoules per kilogram degree Kelvin. Do I use the CP or the CV? Yeah, I do. Okay. So CV is going to be 0.653 kilojoules per kilogram degree Kelvin, and CP is 0.842 kilojoules per kilogram degree Kelvin. And the point, almost the point of all of these transient problems is just try to kind of play a mind game with you. We're going to say that it's an adiabatic process, therefore Q is going to be equal to 0. We already know that work is going to be equal to 0 because there's nothing to make it do anything. It's initially empty, so M1 is equal to 0. All these assumptions and all these words are going to cancel things out. So the transient equation that we've been using, we'll say on the left-hand side, is what happens in the storage thing, right? So we have M2 times U2 minus M1 U1. It's going to be equal to this Q between 1 and 2 minus the work between 1 and 2. And then, because we're not going to worry about potential kinetic energy or potential energy, we just jump to M incoming times H incoming minus M exiting, H exiting. All right, so first off, that's going to be 0. And that's 0 because just as we said, M1 is 0, so that's going to be 0. There's nothing exiting, so that's going to be 0. So what we're looking at right here now is really just M2U2 is equal to MIHI, which is these two are going to be equal to each other, so they can just cross out. So you just say that the internal energy is going to be equal to the enthalpy that's inside here. If you use specific heats to find these things right here, you're going to have CV times T2 is going to be equal to CP times T. I'll call it I. A lot of times we'll call this the I, or the PI and TI, because they're things coming in. Or we might even call it, yeah, I think that's fair. Yeah, just calling these are things that, we don't want to call it 1 because that's what was inside the tank. So yeah, so all we have to do for T2 is equal to CP times CV, And got to be careful when doing this type of thing. Make sure that you use, because there's a ratio here and a multiplier, and it's not going to be the same if you use regular old degrees Celsius. You have to use absolute temperature. So here you go. And by the way, CP over CV is actually a thing. It's called K. We haven't used it yet, but we will soon. I'm pretty sure it's in different processes that we'll use. K will pop up, but the specific heat ratio is a useful and commonly used thing that you'll have to do. So this times the 400, and what we end up finding is it's going to be 515.8 degrees Kelvin, which ends up equaling 242.8 degrees Celsius. So there you go. There's a pretty good transient example, and not as crazy as the previous ones, which I don't recommend even bothering to watch. But I recorded them, so we're going to leave them up and go ahead and get all kinds of people to say nasty things about me, which is kind of makes me sad, but I'll survive. Okay, so here's a weird one right here. This okay, so well, it's not that weird. What is 400 degrees Kelvin? Is that 123? Is that right? 123 degrees Celsius. For whatever reason, we're redoing this with 20 degrees Celsius and using the table. But so we're not going to be able to compare the results. But let's just take a look at them anyway. So we're going to go to table. Decided to go capital letters for that table this time. B.3.2. Because I said to use B3, right? And so this is for the CO2. And if you go at, what I think it's probably because those values, I'm trying to talk and write at the same time. Those values probably aren't in this table, and they just liked that particular one. And you got T equals 20 degrees Celsius. Okay, cool. At those, you get an HI of 381.72 kilojoules per kilogram. And so we have the same thing going on right here. We have to say that U2 equals HI. So we just found HI from the table. So now we got to try to find U2. We have to look up and find a place when we're assuming that we're still at 800 kilopascals. We have to find the temperature when U is equal to 381.72, right? That's the goal that we have set out for ourselves. And so if you look in the table, you'll find we have at temperature up here corresponding to under here we have 80 degrees Celsius, and U is 371.37 kilojoules per kilogram. And then at 100 degrees Celsius, U is equal to 386.11 kilojoules per kilogram. So if you interpolate right there, you find that T is equal to 94.0 degrees Celsius. And so that's the answer. Not as satisfying that we can't compare these two. I did something else here, though, is to look up at this temperature, right? So we have 400. So that turns out to be what 100. I said 123 degrees Celsius. Well, we have a nice little fluid calculator thing here from the fine people of IRC. I don't know who they are, but I think it might be a college. I don't know. I'd like to go meet them. Say thank you. That was nice of you. So we have the absolute pressure 800, and we're getting a temperature of 123. Yeah, 123. right? So now they do their enthalpy and their entropies not by kilojoules per kilogram, but by joules per kilogram. So I'm going to take their enthalpy and I'm going to copy it into here. So it's that value right here. I'm going to copy it, and now I'm going to change this thing into internal energy. I'm going to paste, and we'll hit the boom. And what we find, we get 215 degrees compared to what I found from the specific heat. So that didn't do too well. You know, that was from their tables. We couldn't use our tables because our tables don't go up that high, and I don't think there's something wrong with our tables. That's what I took from that. We could do the same problem that we did just a second ago, and so like see, I'll go temperature, and of course, what did we have? We had 20 degrees Celsius. It wouldn't let me do it. 20 degrees Celsius. Boom. And so here's our enthalpy, boom, right there. And now let's turn that into internal energy. And find it, and there you go, 94. Oh man, we got a lot better than that one, right? That one worked out a lot better, 94. So I don't think this specific doing this method right here works all that well for carbon dioxide. That's my near-term conclusion. End of example.